Light is everywhere. It allows us to interpret the world around us and is a crucial requirement for life on Earth. But what is light? This is one of the fundamental questions of quantum physics, and even Einstein had difficulty wrapping his brain around it. Hi, I'm Rich Burnett for Wondrium. In this episode of Perspectives, three scientists discuss groundbreaking research that led to our current understanding of the quantum world. We begin now, in the early 19th century, with a famous experiment that provided our earliest understanding of the true nature of light. Enjoy.
What Young did was to have two adjacent slits in a screen with another screen much further away. If light is a wave, then what would happen is that it would pass through the two slits. The light passing through one slit would spread out as it moves to the distant screen. The same thing would happen to light passing through the second screen. Since you have two sources of waves, these two sets of waves can interfere with one another. We say that the waves constructively interfere if the two waves enhance one another to make a bigger wave, and they destructively interfere if the two waves cancel each other out. It takes a little math to work out where the waves would constructively and destructively interfere, which I'll skip. I'll just show you what it looks like. If the slits are thin and placed close to one another, you can treat the point between the two slits as the center, and what you see is that waves coming out at certain angles constructively interfere, while other angles destructively interfere. You should note that there are many angles for each. So, what would you expect to see on the distant screen? You'd expect to see bright spots where the waves add together and dark spots where they cancel. That's a clear prediction of wave theory. This is a clear difference in the prediction of the behavior of what waves would do and what particles would do. So what did Young see? What he saw was a clear indication that light was acting as a wave. There is really very, very little wiggle room. From 1801, the scientific community accepted that light was a wave. However, in the late 1800s, a mystery arose involving light and electrons. Light carries energy. You know that because, for example, you can get a sunburn, which is when your skin is damaged. Moving to atoms, you can think of electrons as being held tightly to atomic nuclei. In very crude terms, they're like balls tied to a post by a string. In that analogy, the post is the nucleus, the ball is the electron, and the string is what holds the electron to the nucleus. In our analogy, if you bang into the ball hard enough, you can break the string and the ball will fly away. Similarly, if you shine a bright light on a material made of atoms, it is possible to knock off electrons. This is called the photoelectric effect, and scientists have known of this for nearly 2 decades before it was explained. However, when the photoelectric effect was studied in detail, there were some mysteries, specifically 2 features. The first is puzzling. Certain colors of light will knock out electrons and others won't. The exact color depends on the substance, but roughly speaking, red, orange, yellow, and green just won't do it. Blue, purple, and ultraviolet will. Even at the time, physicists knew that different colors had different wavelengths, with the red, orange, and yellow side having a long wavelength, and the blue, indigo, and violet side having a short wavelength. And each material had a specific wavelength above which electrons would not be emitted, and below which they would. So that was a bit weird, but it was compounded by the fact that it didn't matter how bright the light was that you used. The wavelength thing was the barrier. You could use really super bright red light and you'd get no electron emission. But use weak purple light and voila, electron emission. And if you turned up the brightness of purple light, you'd get more emission. Now, if light is a wave, that's a weird thing, because the energy of a wave depends on what physicists call its amplitude, or colloquially, its brightness. It's kind of like waves on the beach. Little wavelets don't do much damage, but get a 6-foot tall wave and they'll knock you on your keister. And tsunamis with really high waves will knock over buildings. The height or amplitude of the wave governs its energy. So that's a weird thing. It means that in the photoelectric case anyway, light isn't acting like a wave. The situation was resolved in 1905 by none other than Albert Einstein. Einstein proposed that light came in discrete lumps, which is a fancy way to say in particle form. The energy of each lump was proportional to the frequency of light. Frequency is inversely proportional to wavelength, so a long wavelength wave has a low frequency, while a short wavelength light has a high frequency. Thus, the light on the blue, indigo, violet light was high frequency, which, according to Einstein, meant high energy. Also, let's think about what it means and how the particle idea explains the data. If light is a particle and the energy of the light is proportional to the frequency, then below some frequency, the individual particles of light, what we call photons, just don't have enough energy to knock out an electron. Getting back to the analogy of a post, ball, and string, if you throw an object at the ball and it doesn't have enough energy, it won't break the string. But any photon with higher frequency, which is to say higher energy, will be able to do so. So you can perhaps see why Einstein's idea was so powerful. In fact, it was his explanation of the photoelectric effect that netted him the Nobel Prize in Physics. It wasn't relativity. All right, now we're in a pickle. Thomas Young proved quite convincingly that light is a wave, while Einstein just as convincingly showed that light was a particle. Light can't be both a wave and a particle, can it? And this gets even weirder. If Einstein is right, how can we explain the Young double-slit experiment? To take another look at the Young experiment, researchers tried a variant of it. They started by just reproducing Young's interference result. Nothing had changed in the intervening century. But then they turned down the intensity of the light so low that only one photon was emitted at a time, and they shot the light at a pair of slits and looked for the photon on the distant screen. Let's talk for a moment about what you would expect for both the particle and wave scenario. If light is a particle, it would appear at a specific spot on the screen like a bullet hitting a wall. If light is a wave, it would appear in the wave pattern, just very, very faint. Then photon after photon, the pattern would get brighter and brighter. So what did they see? They shot the first photon, and it turned out, a drum roll please, it appeared at a single spot. It was like a particle. But that's just totally weird, since a bright light on two slits resulted in Thomas Young's wave pattern. So they continued their experiment and they shot a second photon, still detected like a particle. Okay, then another and another and another. Let's just fast forward and see what the final result was. After millions and billions of photons, what they found was the wave pattern of the double-slit experiment.
I wonder which way electrons behave. So let's rerun our experiment with the electrons, and let's add a way to keep track of exactly which of the vertical holes in the wall each electron goes through. If they're really acting like particles, then we ought to see that as each electron passes through one and only one of those gaps. If they're acting like waves when they get to the wall, well, let's just see what happens. First, we need some way to keep track of which vertical gap each electron is passing through. One way to do this is to put a light source near each slit. That way, if an electron passes through, say, the gap on the left, then that electron ought to scatter some of the light over there, and we'll see a flash near the gap on the left. We'll also need to leave some sort of triggered camera next to each gap, something that will record a flash if it happens. So now we've updated our measurement-taking devices. Now, when we send electrons toward the wall with the two slits in it, if an electron passes through one gap or the other, our light sources with triggered cameras will capture the event, and they'll tell us which gap the electron passes through. And if the electron continues on its path, it'll then hit the back wall and mark our strike paper. In this way, we should be able to keep track of everything we're interested in all at the same time. So now imagine, with this more sophisticated setup, sending electrons toward the wall that has two slits in it. As we do so, we'll see flashes of light, and we'll hear the camera click as each electron passes through one hole in the wall or the other. That seems very reasonable. Well, let's continue sending electrons in that direction until we think we have enough statistics to go ahead and check what's going on at the back wall. So, what do we find? Well, this is strange. After we sent through electrons, we check to see on the back wall and see that everything has changed. We've lost the interference pattern on the back wall. Now the pattern on the back wall looks just as though we had sent tennis balls through it. The frustrating thing here is that the very act of measuring and keeping track of which opening each electron went through destroyed the interference effect. And it turns out that there's just no way around this. You might think, oh, we just need to turn down the intensity of the light source. Maybe we used light that was too bright and it disturbed the electrons too much. What you'll find as you turn the intensity of the light down is that at some point there won't be enough intensity left to see the electrons anymore, and then just about the time when the light is no longer bright enough to tell you which electron went through which opening, you'll recover the interference pattern. Or you might think about changing the color of the light instead of the intensity. Now, since longer wavelength light carries less energy, maybe it will disturb the electrons less. So let's try that. What if we try changing the wavelength of the light used to measure which electron goes through which opening? In this case, we'll see that the same types of limitations come up. If we make the wavelength longer and longer, hoping that that will disturb the electron less and less, we'll see that when we reach a wavelength long enough to recover the interference pattern on the back wall, now we can no longer tell which of the openings the electron went through. Sure, now we have our interference pattern on the back wall again, but at these long wavelengths, the flash we see will be so diffuse and spread out that we can't tell which gap the electron went through. It really does seem like this is something we are stuck with. If we find a way to measure which opening the electron went through, the interference pattern is destroyed. But as long as we don't check on exactly how the electron gets through the gaps in the first wall, there will be an interference pattern on the back wall. These things really do act like particles and like waves at the same time.
Throughout the mid and late 1920s, a great deal of effort was directed toward developing a rigorous system of mathematics that could be used to describe and calculate how quantum particle waves behave and interact. In 1925, for example, Erwin Schrödinger developed an equation that describes the wave-like behavior of electrons. The Schrödinger equation is still taught today to nearly all undergraduate physics students, and it makes accurate predictions, at least for electrons that are moving at speeds far below the speed of light. And Schrödinger wasn't by any means the only scientist to make progress in this direction. Many other physicists, including Paul Dirac and Werner Heisenberg and Max Born, each made important contributions around the same time. This new generation of quantum theorists was not content with the old quantum theory as developed by Einstein, Bohr, and de Broglie. They were intent on building a more complete and more mathematically robust system. This system would become known as quantum mechanics. As this system of quantum mechanics was being developed, Einstein found himself more and more troubled by its implications. At least with the concept of light quanta, there was some notion of what it meant for light to be a wave. It had been long established that light consists of oscillating or vibrating electric and magnetic fields. And the peaks of a light wave are those points in space where the electric and magnetic fields are the strongest. But when it came to something like an electron wave, it wasn't at all clear what the peaks of the wave really represented. The key question about matter waves, and the question that was bothering Einstein, was the following: what exactly is waving? A classical wave makes sense because it's made up of many objects. A water wave, for example, is the highest at one point because there are the most water molecules at that point. But the wave of a single electron can't be interpreted in terms of the collective behavior of many objects. It's only one electron, after all. One object can't exhibit the kind of collective behavior that a water wave does. In 1926, Max Born proposed a very radical answer to this essential question. Born argued that the shape of the wave of an electron or of any other quantum object, called the wave function, should be interpreted to represent the probability of that object being found in a given location, when or if it were measured. If you conduct an experiment to determine the location of a given electron, there's a high probability that you'll find it somewhere where the absolute value of the wave function is very high. There's a much lower probability that you'll find it in a place where the absolute value of the wave function is low. As Born saw the problem, there's no choice but to view the wave of an electron in terms of the probability of it being found in a particular location or in a particular configuration. And this soon became the standard way for physicists to think about matter waves in quantum mechanics. Let's take a second to step back and ask what this really means. According to Born and his way of thinking about quantum mechanics, how should we think about the electron as it exists prior to being measured? Well, in some sense, according to Born, the electron is extended across the volume of space that is covered by the wave function. When we measure the location of an electron, it's always point-like, without any spatial extent. But before it is measured, an electron is simultaneously in all of the locations it's covered by its wave function. It's in many places and all at the same time. In this sense, electrons and other quantum objects have a kind of probabilistic existence, being in all possible places and doing all possible things at all possible times. This is sometimes described in terms of what is known as the Heisenberg uncertainty principle. According to this principle, the more precisely defined the location of a quantum object is, the less specified is its velocity, and vice versa. According to quantum mechanics, an object cannot be in only one place and moving at only one speed. At this point in time, you're probably feeling a bit confused, and you should be. This is bizarre and incredibly counterintuitive stuff. Quantum mechanics describes a kind of existence that is beyond strange. And it's fundamentally different from anything that we as human beings normally experience. As Niels Bohr once famously remarked, anyone who is not shocked by quantum theory has not understood it. In December of 1926, Einstein wrote a letter to Max Born expressing his skepticism of the new interpretation of quantum theory. In this letter, Einstein made one of the most famous and often quoted remarks. Let me read you just a few sentences from this letter. Quantum mechanics is very impressive, but an inner voice tells me that it's not yet the real thing. The theory says a lot, but does not bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not play dice. Einstein expressed sentiments similar to this one on many occasions throughout his life. In various ways, Einstein became fond of insisting that God does not play dice with the universe. In the late 1920s, a consensus was starting to form around a refined version of Max Born's interpretation. This view became known as the Copenhagen interpretation, named for the city where Niels Bohr, Werner Heisenberg, and others had made major contributions to its development. According to the Copenhagen view of quantum mechanics, quantum particles behave like waves. These particle waves are each described by their wave function. The shape of a given particle's wave function represents the probability that it will be found at different locations or with different velocities. Generally speaking, quantum particles exist in multiple locations at once and have multiple velocities all simultaneously. But according to the Copenhagen interpretation, whenever an observation of a particle is made, its wave function collapses, and the measured quantity takes on a single measured value. At the 1927 Solvay conference, it became clear that a consensus view was starting to form around the Copenhagen interpretation. Most of those in attendance seemed to have accepted the probabilistic nature of their new theory. Furthermore, there was a general acceptance that this was likely to be a real aspect of nature, and not something that would be explained away when they better understood the problem. For example, Max Born, Werner Heisenberg, and Niels Bohr were each fully aware that the universe as described by quantum mechanics was fundamentally probabilistic. And while they acknowledged that there was still some chance that determinism could somehow be restored in some future revision of the theory, they each thought that this was pretty unlikely. Unlike Einstein, they were prepared to accept the lack of determinism in the subatomic world. Einstein was unwilling to accept any version of quantum mechanics in which God played dice with the universe. And when Einstein declared this, Niels Bohr simply replied by telling Einstein to stop telling God what to do.
Hey, thanks for watching. If you'd like to learn more about the topics in this episode, the full list of series that these clips came from is in the description below. You can watch them all on Wondrium. And don't forget to subscribe to this YouTube channel for new episodes of Perspectives, and you can watch previous ones here.